Okay, now let us discuss about Faradays and Henry experiments in electromagnetic induction. Faraday and Henry, what experiment they did, and from that what laws they produced, that I am going to explain. For that, the first experiment did by the Faradays and Henry is that they took one coil. This coil or the wire loop connected to one galvanometer and one magnet is moved along the axis either towards or away. Okay, look at here, the magnet is moved. When the magnet is moved, then what happens in this? When the magnet is moved towards the coil, the magnetic field lines are there. Right? When we move the magnet towards the loop, at that moment what happens? When the magnet comes nearer to the loop, the field produced by the magnet will be increases. The field link with the loop, the magnetic field link with the loop will be increases, because when the magnet comes closer, the more lines passes through it. Okay. And one more thing is that when the magnet distance, for example, at this point, if you want the magnetic induction, this loop is in the magnetic field produced by the bar magnet. But this magnetic field on the axis, this is a north pole, this is south pole. On the axis, the magnetic field formula is, in case of short dipole, nu naught by 4 pi into 2 capital M by R cube. Field inversely proportional to the cube of distance. That means when the distance decreases, then the field will be increases. This is the distance, R is the distance. When the distance decreases, the field is increases. But the flux link with the loop, okay, right? This loop is in the magnetic field of bar magnet. When the bar magnet is moved towards the loop, the field link with the loop will be increases because of decrease in distance. When the field increases, automatically the flux also increases. Okay, because the flux is proportional to field. Then that means when we move the magnet, the flux link with the loop changes, but the change in flux, okay, produces the EMF or current in the galvanometer, okay, in this loop. Due to that, here they observed the deflection in the galvanometer. Practically, they observed the deflection in the galvanometer. Okay, right. What happened at here? When we move the magnet, the magnetic flux is changing. Due to the change in magnetic flux in this coil, either current or EMF induces. Due to that current, here the galvanometer deflects. Here this is observed when they moved the magnet. After that, they moved the magnet away from the loop. Even though they observed that the galvanometer again deflects, but when they keep the magnet and loop both are at rest, then they not observed any deflection in the galvanometer. That means the final conclusion is that, okay, when we move the magnet either towards the loop or away from the loop, the galvanometer deflects, but the deflections are opposite. When we move the magnet towards the loop, if the deflection is in one direction, and when we move the magnet away from the loop, the deflection in the opposite direction to the first one. Okay, the reflection direction is changing. From this, instead of one more thing they did, that instead of keeping the first loop at rest and magnet in motion, and they kept the magnet at rest and they moved the loop, and they also observed the same thing. That means the final conclusion from this experiment 1 is that the relative motion between the magnet and the loop induces current or EMF in the loop. The relative motion between magnet and loop induces current or EMF in the loop, right? Okay, this is the conclusion. This is the experiment 1, and they did some other experiments also, right? Now here what they did, the experiment 2 is that this is a coil. It has the galvanometer, and this is another loop. This has a battery with plug key. And this plug key is closed. Then some current passes through it. And this is the coil 1. And this is the coil 2. Now the coil 1 either moved towards the coil 2 is moved towards the coil 1 or away from the coil 1. Okay, look at here, they are taking the two coils. In this first coil, the first coil has only galvanometer. That means in this there is no battery. The galvanometer should show the zero deflection, no current. But in the second coil there is a battery, some current passes. When this current passes through this coil, this will act as a magnet. Now the coil 2 is moved to either towards the coil 1 or away from the coil 1. Then this will act as a magnet when it is moved towards the coil 1 or away from the coil 1. Then it will be exactly similar to this one, because here we are taking the direct magnet and here we are taking the indirect magnet, because whenever current passes through this coil, it will also act as magnet. Then it is moving here, that means the same phenomena happens and the galvanometer deflection occurs in this. And in this what they concluded, that the relative motion between these two coils also produces the current or EMF in the coil. This is the observation. What they are doing here, relative motion between the two coils. In these two coils, okay, here this first which coil is generating the magnetic field here? This coil is generating the magnetic field, right? Like this the field lines will be produced. The field lines produced by them, okay, that is depends upon in link with this loop, okay, then that's why the flux links, and then it can act as a magnet, and this is a north and this is south, okay, like this field lines will generate. And now the relative motion between the second observation is that the relative motion between two coils produces or induces current or EMF, okay, in coil 1. Look at here, in these two coils are there. But here you can move either the coil 2 or coil 1. You observe the same thing. That means galvanometer is deflecting. But if you keep the 2 are at rest, then it will not give any deflection. That means compulsory any one of the coils should be moved. That means the relative motion between one coil with respect to another coil produces the EMF. Right? And the next, let us go for the one more experiment, that is experiment 3, that done by the great scientists Faraday and Henry. What is that? Let us see. They took like this. This is some soft iron or anything. And here one insulated wire, right, and insulated coil, this is wound like this. And here one galvanometer is connected, and here one more thing, coil is there, okay, and this coil is connected to the battery and with a plug key, okay, this is the plug key. And here these two coils are at rest in this, coil 1 and coil 2. Okay, both are at rest. In this case, both coils are at rest. But even though, right, how these are insulated, okay, this is some soft iron like this, soft iron. Okay, I will explain the arrangement in this. This is one insulated copper wire. It is connected to the galvanometer. This is insulated copper wire. It is connected to the battery and a plug key. When the current, there is no direct link with these two coils. And now why we are using these two coils, I will explain. Here when we close this plug key, what happens? The current in the coil 1 increases. Is it right? The current in the coil 1 increases. Sorry, not coil 1, coil 2 increases. When we close the plug key, the current increases from 0 to certain maximum value, right? The 0 to certain maximum value, okay. And now but it takes only fraction of seconds. In the fraction of seconds, due to this battery, for example, I current passes. If there is no battery and plug key is open, then the 0 current. But due to the battery, I current, when we close the plug key, the current increases from 0 to I in that instant. Now at that instant, when current increases, then the field will be increased, because the field produced by it is also linked with the another coil. Then when the current changes, then the field changes, okay, because the field is mu naught Ni, field proportional to current. When current changes, field changes means flux changes, because flux formula is dA cos theta, flux proportional to B, right? What happening it here? When current changes, magnetic field changes. When magnetic field changes, flux changes. That change in flux induces EMF or current in the coil 1, right? Whenever they observed the deflection in the galvanometer, when they close the plug key, instant deflection goes to side and then come back to 0. Okay, galvanometer will be like this there. It can use it to measure the small currents. The galvanometer shows the 0 at here, and this side lines will be there and this side lines will be there. And when they close the plug key, the deflection occurred this side and instantly it will come back. Why? Because here when they close it, at that instant the current increases to certain maximum value, later constant. When the current increases to certain maximum value, at that time field increases, flux increases. In this, that flux is linked with this loop also, okay. The change in magnetic flux in the coil 2 link with the coil 1. That's why when the magnetic flux link with the coil 1 changes, then in this EMF induces, that phenomena is called as electromagnetic induction, and then galvanometer deflects. When they opened the plug key, again the deflection observed, that is opposite to the first deflection while closing. And when they opened, what happens? Current decreases from maximum value to 0. At that moment current decreases, the field decreases, flux decreases. Then again the decrease in flux generated by the coil 2 also link with the coil 1. Due to that, the decrease in flux, change in flux induces the EMF or current in the coil 1. Okay, then in coil galvanometer deflects. But when it comes to 0, later the current remains 0 and it will be constant, then the 0 current, then it cannot produce any deflection. That means just at the instant when we close the plug key, then the galvanometer in this EMF produces, but come back to needle pointer deflects and come back to 0. And next, when they open the plug key, then deflects in opposite direction, again instantly come back to 0. That means just at the instant of closing and opening the plug key, only the deflection occurs. This is the experiment 3. Okay, in this experiment 3, what happening it here, when they closed and opens the plug key, and at that instant, okay, the EMF or current induces in the coil. When plug key close, while plug key closing and opening, right, when plug key closed or open, at that instant galvanometer shows deflection, and immediately returns to 0. Right, later galvanometer shows 0 deflection. This is the 3 Faraday's experiment. Just simply in this first experiment, they moved the magnet, then they observed the deflection in the galvanometer, some current is inducing it here. That means when we move the magnet, the current is inducing. When we move the magnet, what happens? Field changes, flux changes, right? Change in flux induces the current or EMF. Due to that current, galvanometer shows the deflection. Here also, instead of moving the direct magnet, we are moving the current carrying magnet. Current carrying solenoid is a magnet. Then when we move it, the same thing will happen. And the third experiment 3 is that, okay, here in 2 experiments, they are moving the magnet or coil. But in this, the 2 coils are at rest. But when they closed and opened, at that moment, at that instant, the current is changing in the coil too. The change in current generates the change in magnetic field. Then that change in magnetic field changes the flux. That change in flux link with the coil 1, and due to that change in magnetic flux, EMF produces and current produces, the galvanometer deflects. That means in these 3 cases, what happening and what is the conclusion that observed the Faraday, and he gave some laws, right? Okay, that are the Faraday's laws. I will explain the Faraday's laws. Okay, and take the screenshot and note it. Okay, let us see what is our topic now. Faraday's laws, right? What are the Faraday's laws? Faraday's laws, very important. Okay, right. Now first law, there are 2 laws are there. First law is very simple. Whenever the change in magnetic flux occurs in the coil, then what happens? Current or EMF induces in that coil. That is called as first law. That's all. Whenever the change in magnetic flux occurs, for example, this is a coil and this is the magnet. When you move the magnet towards the coil, what happening? Magnetic flux link with the coil changes. When magnetic flux changes, then EMF or current induces in that. The first law is that whenever change in magnetic flux, whenever change in magnetic flux link with a coil, then EMF or current induces in it. EMF or current induces in it. Induces in it. Simple. The change in magnetic flux induces current. Okay, when the magnetic flux changes, then the current induces. This is the Faraday's first law. Okay, the first law is that whenever the magnetic flux link with a coil changes, then EMF or current induces in the coil. This phenomena is called as first law. Okay, right. Second law is what? The second law is also very simple. The first law says that the change in magnetic flux produces current. Then he gave the relation between the change in magnetic flux and induced EMF. That is, in the second law is that induced EMF is equal to the negative rate of change of induced EMF is equal to the negative rate of change of magnetic flux. Okay, induced EMF in a coil is equal to the negative rate of change of magnetic flux. That is, induced EMF we write here, induced EMF, okay, we write as minus d phi by dt, and this we write if coil has, okay, induced EMF across a coil which has capital N turns, right? Then that is induced EMF is equal, we write as minus N d phi by dt, we write d phi by dt. We can also write like this sometimes, minus d by dt of n phi. Okay, right. Let us see here what is phi in this. Phi is the magnetic flux link with only one loop. Magnetic flux link with one loop. Link with each turn, only one turn of coil. Phi formula is here B bar dot A bar. Its formula is BA cos theta. Okay, right. This is, we can also write here like this, induced EMF is equal to minus d by dt of here n phi, phi is the BA cos theta. Now this is the Faraday's second law. That means you may keep anything, you can change either number of turns, field, area and theta. If you will change any one term in this, then here what happening? Flux changes. This is totally flux. Bracket term is the flux. We can change the flux by changing the number of turns, field, area, angle, right? When any term will be changes, then EMF induces in it. This is the formula for induced EMF. Okay, And one note point I will give, that is the important point. Induced EMF formula we derived, right? Okay. Induced EMF formula is what? Induced EMF in a coil. Induced EMF, right? What is it? E is equal to, we write as induced EMF in loop. Okay, loop I want. Loop has only one turn, right? Then we write as E is equal to only minus d phi by dt we write. Why? Because the loop means it has only one turn. Then I want the induced charge. Induced charge, what happens? Induced charge I want. When you know the EMF, how to get the charge? Okay, how to get the charge? EMF we write as induced charge. EMF is nothing but V. V is equal to, we write as IR. Okay, induced EMF is equal to IR we write. Okay, induced EMF is equal to IR we write. I we write as dq by dt. E is equal to IR. IR is the dq by dt. Okay, IR, I we write as dq by dt into R. Okay, this dt will cancel, and then simplify, you can simplify it. Okay, and we can go for some more steps. I will rub this side and I will continue. That is, in the note point I am going to give, that is induced charge. Induced EMF in a coil. Okay, right, I will write everything it here. Note point. Induced EMF, induced EMF, induced EMF in a coil or the loop. Its formula we know, that is minus n d phi by dt or minus d phi by dt of n phi or n d phi by dt. Okay, and induced charge I want, he we write as IR. IR is equal to minus n d phi by dt, but I we write as dq by dt, rate of flow of charge is the current. Okay, here we are writing the E. E is nothing but V. V is equal to IR we write, where R is the resistance. Minus n d phi by dt we write, and here dt will cancel. Then dq is equal to, we write as minus n d phi by R. Okay, right. And this is the total charge. If this is the induced small amount of charge, if you want the total charge, induced charge, induced total charge, if you want, dq means a small amount of charge, we have to integrate on both sides, right? Then this is nothing but induced charge is equal to integration of minus n d phi by R. Okay, right. Then what integration it will use? So initial flux phi I, final flux phi F. Then we write here minus n into n by R into integration d phi. What is integration d phi? N by R is a constant. Integration d phi we write as phi minus n by R into phi. Limits we write as phi I to phi F. Now substitute it. Minus n by R into phi F minus phi I we will get. Then you multiply with n, multiply with minus, then we will get some formula for the induced charge. The induced charge is equal to n by R into phi I minus phi F. Okay, this is the final formula. Okay, this is nothing but induced charge is equal to Induced charge is equal to, what is this? Change in flux. Change in magnetic flux. Change in magnetic flux by resistance. Change in magnetic flux by resistance. Let us go for the turns here. N is what? Number of turns. Number of turns in coil. What is R? Resistance of coil. What is phi I? That is nothing but BA cos theta. Initial magnetic flux. Link with only first loop, one loop. This is the final magnetic flux. Link with only one turn. Why one turn? Already we are taking n, multiplying with n means that is n. Phi is the flux link with one turn, n phi is the flux link with n turns. Okay. So this is about Faraday's laws. In Faraday's law, that is a negative sign is there, right? That negative sign in the Faraday's law explained by, okay, negative sign in Faraday's law explained by negative sign in Faraday's law explained by Lenz's law, that we are going to discuss in the next class. Okay, thank you for watching my lecture.